Welcome students. In this session I am going to explain about CPU scheduling. So here in this video we will see criteria of CPU scheduling and preemptive, non-preemptive schedulings and type of queues available. So the CPU scheduling is the activity of the process manager that handles the removal of the running process from the CPU and the selection of another process on the basis of a particular strategy. So a process is running in the CPU, a CPU is a resource. So we are giving CPU to the process. So the selection of another process. So from running process we have to remove the running process and then we have to give the CPU to another process based on particular strategy. CPU scheduling is an essential part of multi-programming operating system. Here multi-programming where more than one processes are loaded into the memory. What is multi-programming? More than one process can be loaded into the memory. Such operating systems allow more than one process to be loaded into the executable memory at a time, and the loaded process shares the CPU using time multiplexing. And scheduling criteria. So different CPU scheduling algorithms have different properties, and the choice of a particular algorithm depends on various factors. Many criteria have been suggested for comparing CPU scheduling algorithm. We have various algorithms and based on scheduling criteria. So we have to learn about some important terms here. CPU utilization. The main objective of any CPU scheduling algorithm is to keep the CPU as busy as possible. Theoretically, CPU utilization can range from 0 to 100%, but in real-time systems it varies from 40 to 90% depending on the load upon the system. So we have to keep the CPU busy. Okay, that's the first criteria. And then throughput. Number of processes executed and completed per time unit by CPU. Okay, it is a measure which number of processes completed per time unit. For example, if I say within a minute the CPU executed 5 processes, then the throughput is 5. If for 30 seconds, for within if I take unit of time as 30 seconds, within 30 seconds CPU executed 10 processes, then throughput is 10. This is called throughput. The throughput may vary depending upon the length or duration of processes. And then turnaround time, overall time. Okay, for a particular process an important criteria is how long it takes to execute that process. The time elapsed from the submission of a process to the completion is known as the turnaround time. From the submission, from the creation of process until it is completed. So it is the turnaround time is the sum of time. It is a sum of time spent waiting to get into memory, waiting in the ready queue, executing in the CPU, and waiting for input output. So turnaround time is the sum of all the waiting time, all the amount of time during waiting, executing. Burst time, we have execution time or burst time, and waiting for input time, input output time. So we have to sum all these into turnaround time. Turnaround time can be calculated by completion time minus arrival time. So here arrival time is submission time. Arrival time is submission time. So completion time minus arrival time is equal to turnaround time. And then waiting time. A scheduling algorithm does not affect the time required to complete the process once it starts execution. Okay, it only affects the waiting time of a process, that is time spent by a process waiting in the ready queue. Okay, it does not affect the completion time, but it affects the waiting time. We have many algorithms, so each algorithm will have average waiting time based on some criteria. Okay, so waiting time can be calculated by turnaround time minus burst time. So here turnaround time we have found it earlier. Turnaround time is completion time minus arrival time. So turnaround time is overall time including burst time. You can see including execution in the CPU. In turnaround time, execution in the CPU or burst time is also included. Here burst time is not affected. Execution is not affected. It only affects the waiting time. So we have to subtract burst time from turnaround time to obtain waiting time. The average waiting time is determined by summing the respective waiting time of all the processes and divide the sum by total number of processes. Okay, here if for example we have 5 processes and sum of all the processes waiting time. Sum of all the processes waiting time is 30. So 30 divided by 5 is 6. 6 is the average waiting time. This is how we have to find the average waiting time. Response time, another criteria. In an interactive system, turnaround time is not the best criteria. A process may produce some output fairly early and continue computing new results while previous results are being output to the user. Thus, another criteria is the time taken from submission of the process of request until the first response is produced, not the exact output. So if we submit the process and the process started responding, it's started to give outputs. Okay, so we can use another measure which is response time. For example, when we apply to a company and we expect a company to reply, it's not exact output. We don't get a job, we may or may not get the job, but we get the email from the company saying we received your email, just like that. It's a response time, first response from the process. And then preemptive and non-preemptive scheduling. We have two types of scheduling. Non-preemptive, simply a process will not give the CPU to other processes until it is completed. Simply, process will not give the CPU to other processes until it is completed. That is non-preemptive. Non-preemptive scheduling is used when a process terminates. It is used when a process terminates or a process switches from running to waiting state in two scenarios. Either a process terminates or switches from running to waiting state. In this scheduling, once a resource, here CPU cycles are allocated to a process, the process holds the CPU till it gets terminated or reaches a waiting state. In the case of non-preemptive scheduling, uh, scheduling does not interrupt a process running CPU in the middle of the execution. Instead, it waits till the process completes its CPU burst time and then it can allocate the CPU to another process. In simple words, if a process is allocated to a process is allotted to CPU is given to the process, then the process will not leave the CPU until it is completed. That is non-preemptive. We have some algorithms here: first come first serve algorithm, shortest job first algorithm, and non-preemptive versions. Okay, these algorithms are based on non-preemptive. And then preemptive scheduling, exactly opposite of preemptive scheduling. It is used when a process switches from running state to ready state or waiting state to ready state. From running to ready or waiting to ready. The resources, mainly CPU cycles, are allocated to the process for a limited amount of time and then taken away. And the process is again placed back in the ready queue if that process still has CPU burst time remaining. That process stays in the ready queue till it gets its next chance to execute. So, for example, even if some of the CPU burst time remaining, we are going to remove the process from the CPU. For example, round robin scheduling. Here each process holds a predetermined amount of time, so time quantum. So for example, if I say 4 seconds, 4 nanoseconds, each process can run for 4 nanoseconds, and after 4 nanoseconds the process running in the CPU is preempted and another process is loaded into the CPU. And algorithm based on preemptive schedulings are round robin scheduling algorithm, shortest remaining time first. The difference between shortest job first and shortest remaining time first is preemption, and priority, which is preemptive version. So in multiple feedback, multiple queue feedback system, we are going to give priority. If a process is waiting a long time, then we have to give we have to increase the priority of the process. Here it is a preemptive version. And then queues. What are the queues available in the process scheduling? The operating system maintains all process control blocks in the process scheduling queues. The operating system maintains a separate queue for each of the process states, and process control blocks of all the processes in the same execution state are placed in the same queue. When the state of a process is changed, its process control block is unlinked from its current queue and moved to its new state queue. And the important process scheduling queues are here. Job queue. This queue keeps all the processes in the system. For example, long term scheduler. And then ready queue. This queue keeps a set of all the processes residing in main memory ready and waiting to execute. A new process is always put in this queue. And then device queue, the processes which are blocked due to unavailability of an input output device constitutes this queue. So job queue, which is a long term scheduler. From the long term scheduler, the processes are selected and loaded into memory ready to execute in the CPU. It is a ready queue. If and the processes are executing in the CPU, and the process wanted to access input output devices, then it is put into the input output device queue. Okay. And then there is a question here, which of the following is not an optimization criterion in the design of a CPU scheduling algorithm? A, minimum CPU utilization, maximum throughput, minimum turnaround time, minimum waiting time. So here we have to improve the number of processes executing per time unit. We have to minimize the turnaround time. We have to minimize the waiting time. So which is not a optimization criteria is CPU utilization. That's the correct answer. Minimum CPU utilization. That's it for in this video. In next video we will see first come first served and many scheduling algorithms one by one. Thank you all.